Hello everyone. Today, I'd like to talk to you about reduction in communication via image selection for homomorphic encryption-based privacy-protected personal identification. Multiple camera monitoring systems are needed for realizing a safe society. Such systems are useful when searching for a criminal or lost person. We consider a multiple camera monitoring system set in indoor corridors, where pedestrians must pass when moving between rooms. I explain overview of multiple camera monitoring system. First, the camera clients acquire video sequence using a camera. Second, the camera clients detect pedestrian images from the video sequence. Third, the camera clients extract features from pedestrian images. Fourth, the camera clients send features to a server. Finally, the server matches features. In order to correctly match pedestrian images acquired from the same individual, it's necessary to extract features that represent identities from the images. When designing a multiple camera monitoring system, we must pay attention to the fact that features used in personal re-identification are personal information. This is because the features are personally identifiable. To protect the personal information of the features, we focus on homomorphic encryption. Homomorphic encryption enables the distance to be computed using addition and multiplication operations without decrypting the target features. We apply homomorphic encryption to features for person re-identification, and we perform the distance computation while the features are still encrypted. The use of homomorphic encryption causes a severe problem in the multiple camera monitoring system. The amount of communication between each client and the server becomes very large. One factor is data size of features. The data size of features after homomorphic encryption is much larger than that before encryption. So the amount of communication per feature increases. Other factor is number of pedestrian images. The data size is proportional to the number of pedestrian images, which is the stage before the conversion to features. So the amount of communication further increases when the number of images is increased. In order to avoid the problem of the data size, it's necessary to devise ways to reduce the amount of communication. There are two possible ways. The first one is by reducing the number of dimensions of the features. The second is by selecting the features to be sent to the server. We focus on the feature selection approach. We consider reducing the number of pedestrian images before feature extraction. Many pedestrian images are acquired as a person walks in the field of view of a camera client. If all the acquired images are received at the cloud server, the amount of communication increases drastically. We aim to reduce the amount of communication by reducing the number of images. In order to reduce the number of pedestrian images and the amount of communication, we propose a method for selecting appropriate images before feature extraction. We incorporate an image selection approach into a privacy-protected person re-identification system using homomorphic encryption. This is overview of our selection method. We focus on the cyclic motion of leg postures during walking as a cue for selecting pedestrian images. We use a reference leg posture to compute similarity to pedestrian images. Our method extracts the features from the images containing the same appearances of the persons from the cameras. We use the leg posture to select a small number of images from the many images acquired from each client. A person walking in a corridor repeats a cyclic motion of her or his legs. So we assume there will be many opportunities to acquire pedestrian images containing different leg postures. If we acquire a small number of images with the same reference leg posture, we can expect to re-identify a person without decreasing the accuracy. The leg posture of a walking person is represented using spatial and temporal cues. A spatial cue refers to the change of the locations of the body joints. We use the cue of the spatial locations of the body joints shown here. The temporal cue refers to the cyclic movements of the legs of the body joints that change over time. We explain the motion cycle of the leg posture in detail to consider the reference leg postures for image selection. The motion change in the leg posture during walking is called the gait cycle. It's repeated as a cyclic leg movement while walking. The gait cycle is divided into 4 categories according to the differences in the leg postures. The start time of the gait cycle isn't clearly defined. We treat the moment when the left leg leaves the ground as the start time of the gait cycle. We represent each category in time direction from T1 to T4. The duration of one cycle is about 1 second. Categories T1 and T3 are both 40% of the duration. T2 and T4 are both 10% of the duration. We explain how to generate reference leg postures. We represent the temporal cue using each category of the gait cycle. And we represent the spatial cue as the average location of the body joint in each category. We assume the height and angle of each camera set in the corridor are the same. We use 3D locations of the body joints. They are observed by a motion capture system during the gait cycle of many individuals. First, we project the body joints onto the image plane using a predefined perspective projection matrix. Next, according to the definition of the gait cycle, we assign 2D body postures to each category. Finally, we generate the reference leg posture PC for TC by calculating the average values of these 2D body postures. We experimentally determine which of the 4 reference postures should be used. We explain overview of image selection. First, we detect pedestrian images with the locations of body joints from acquired image sequences. Second, we compute the similarity between the reference posture and the detected postures. Finally, we select images for feature extraction if the similarity is more than or equal to a threshold. We experimentally determined thresholds so that one or more images of each person are selected for each client while she or he exists in the field of view. This is overview of privacy-protected personally identification. In step 1, our method selects the appropriate pedestrian images at each camera client using reference leg posture. In step 2, our method extracts from the selected pedestrian images using co-occurrence attributes. Co-occurrence attributes are represented by combinations of physical and adhered human characteristics. For example, a man wearing a suit, a 20-something woman, or a person with long hair wearing a skirt. In step 3, our method applies linear quantization to the features as pre-processing for homomorphic encryption. In step 4, our method encrypts the quantized features using free homomorphic encryption library. In step 5, our method calculates the distance between features using the large margin nearest neighbor. We evaluated the effectiveness of pedestrian image selection using the reference leg posture. We generated the reference postures using AIST gait database. The database measures 3D locations of the body joints using a motion capture system from walking participants. The database consists of 214 healthy Japanese participants. We obtained 2D locations using a manually adjusted perspective projection matrix. We averaged the locations of the body joints of each participant during one gaze cycle, using 100 participants randomly selected from the database. We collected pedestrian images when walking along indoor corridors using 6 camera clients. We used a USB camera and the frame rate was set to 30 fps. The number of participants was 31, but the number of people walking at the same time was limited to 1. There were about 25,000 pedestrian images. We detected the 2D locations of the body joints from images using OpenPose. We used pedestrian images from one camera client as the target, and pedestrian images from another camera client as the query. We used the first match rate to evaluate the accuracy of person identification, and the reduction rate to evaluate the amount of communication. Accuracy of person identification. The vertical line shows the first match rate and the horizontal reference leg posture. The baseline method is using all pedestrian images without image selection. Our method using reference leg postures P2 and P4 obtained better accuracy than the baseline method. Amount of communication, the vertical line shows the reduction rate and the horizontal reference leg posture. The reduction rate is a ratio of the number of images not selected by the method to the number of pedestrian images when no image selection is used. The reduction rate of the baseline method was 0%. Reference leg posture P2 and P4 had a high reduction rate, more than P1 and P3. We believe reference postures P2 and P4, which had a high first match rate and reduction rates, are suitable for the dataset. This is example of selected pedestrian images using reference posture P2 at camera client L4. We listed pairs of pedestrian images and their leg postures picked up from one gait cycle. In person 1, these images were selected. In person 2, these images were selected. We see that the leg postures of the selected pedestrian images are similar to the reference posture P2. We evaluated the amount of communication for the case in which two camera clients send features to the server. The amount of communication per feature increased from 760 bytes to 524 kilobytes before and after encryption. The number of detected pedestrian images were about 5,100 images by each camera client L1 and L2. The amount of communication of encrypted features from all images was 2.68 gigabytes for L1 and 2.65 gigabytes for L2. After selection, the number of pedestrian images was reduced to about 900 for L1 and about 800 for L2. The amount of communication of our method was 0.47 gigabytes for L1 and 0.42 gigabytes for L2. Our method can reduce the amount of communication for privacy-protected person identification using homomorphic encryption. We also evaluated our method on the publicly available MARS dataset. We used the images subset C1 in MARS dataset. We used only those containing more than 20 pedestrian images in one sequence. We evaluated the accuracy of about 4,500 pedestrian images for 41 subjects. We generated reference postures for subset C1 in MARS dataset using a manually adjusted perspective projection matrix. We searched for persons walking in the same direction in the field of view at different times. Other conditions are the same as evaluations on TUP dataset. Accuracy of person identification of MARS dataset. Our method using reference leg postures P2 and P3 and P4 obtained better accuracy than the baseline method. Amount of communication. Reference leg postures P2 and P4 had a high reduction rate, more than P1 and P3. Reference postures P2 and P4 had both good first match rate and reduction rate. This result has the same tendency as evaluations on TUP dataset. To conclude, in order to reduce the amount of communication needed for privacy-protected person identification, we proposed a method for selecting appropriate pedestrian images. We focus on the cyclic motion of leg postures during walking as a cue for selecting pedestrian images. We use a reference leg posture to select pedestrian images. We confirmed that the amount of communication could be reduced while achieving the same or better accuracy of person identification using our method. Thank you for your attention.